In this video, I will discuss proofs in high school geometry. Proofs are one of the more difficult aspects of geometry. I encourage you to come back and watch this video several times until you feel that you really understand proofs. Most people will not be able to fully understand them by watching this video just once. A proof is a set of statements and reasons that should convince someone that a statement is true. I believe that proofs are important for several reasons. First, when I ask a student, "Why did you do that?" I seldom want him or her to answer, "That's what the book told me to do." I would much rather that the student understand what he or she is doing and why he or she is doing it. Proofs are also important because they teach students how to think logically and communicate their ideas. I do believe that proofs are an important part of high school geometry, but I also realize that many students will never understand them. They are not tested on the SAT or ACT, and most students do not see them in college unless they are majoring in a math or science related field. Therefore, many parents, books, and teachers do not teach proofs. If you are using my geometry book as a homeschooled parent or student, I encourage you to attempt the proofs. If you decide that you or your student will never be able to understand them or get them right, it is okay to skip the problems that ask you to prove statements. However, this is not true for all geometry programs, so I encourage you to check with the publisher of your book before you decide to skip these problems. Before we look at some examples of proofs, I'd like to state that different books and teachers can teach proofs very differently. Some books and teachers will want more detail than what you see here, and other books and teachers will want less detail. Also, some books and teachers may state the definitions, postulates, and theorems differently than the way I will state them here. If you have not already done so, please print the document at the website you see here and have it in front of you while you watch this video. The first section on this handout is a list of some properties from algebra. The section titled Points, Lines, Planes, Line Segments, and Rays, and the section titled Angles contain excerpts from our quick reference guides on points, lines, planes, and angles. The third section gives you some proofs for the examples I will discuss in this video. When I am teaching proofs, I like to begin with algebraic proofs because students at this level are generally more familiar with algebra than geometry. So, please pause this video and solve these two equations on your own. Hopefully, you decided that x equals -5 for the first equation. In our first example, we will prove that this statement must be true. However, before we try to prove a statement, it is often a good idea to convince ourselves that the statement must be true. So, let's substitute -5 for x in the original equation and see if we get a true statement. Since this gave us a true statement, this tells us that x can equal -5. However, it does not prove that x must equal -5 in this equation. It is possible that there are other values of x that might work. To prove that x must equal -5 in this equation, we must go through a set of logical arguments that show that this is the only value of x that will work. When we want to prove a statement, we start by stating our given information. Recall that we started out knowing that 4x plus 3 is equal to -17. Now, when you were solving this equation on your own, you probably subtracted 3 from both sides of the equation, so that is what we will do next here. If you look at the handout I told you to print earlier, you should see that the subtraction property of equality allows you to subtract something from both sides of an equation. Therefore, we can say that the subtraction property of equality tells us that 4x must equal -20. When you were solving this equation on your own, you probably divided both sides by 4 next. The division property of equality is the property that allows us to do this. So now we can conclude that x must equal -5 if we start out knowing that 4x plus 3 is equal to -17. Now, let's look at a more complicated example. Hopefully, when you saw this equation earlier, you decided that y is equal to 7. There are several possible ways of proving this statement. I will discuss one of them here, and there is a second, equally correct proof shown in the handout that goes with this video. As you progress through your study of geometry, you will find that there are often several possible proofs of a statement. We must begin by stating our given information. We were told that 5y minus 2 is equal to 3 multiplied by the quantity y plus 4. When you were solving this equation on your own, you probably started by distributing the 3. We can use the distributive property to say that 5y minus 2 is equal to 3y plus 12. Now, when you were solving this on your own, you may have used the subtraction property of equality to subtract 3y from both sides of the equation. Next, we can use the addition property of equality to add 2 to both sides of the equation. Finally, we can use the division property of equality to divide both sides by 2. As I said earlier, there are several different ways you can prove this statement. You may have gone through a set of steps that are different from what you see here. As long as you concluded that y must equal 7, and as long as you can justify each step using a reason from the first page of the handout, your proof would probably be equally correct. Please pause this video and look at the second possible proof on the handout. These two proofs are not the only possible proofs of this statement, but they show the ways that most people would choose to prove this statement. Now, let's look at an even more complicated algebraic proof. There are even more possible proofs of this statement. I will discuss one of them here, and there are 3 more in the handout. To prove this statement, we must start by stating our given information. Next, we can use the distributive property to distribute the 3 to the terms in the parentheses. For our next step, we will use the substitution property of equality. If you look at the first page of the handout, you should find this property towards the bottom of the properties from algebra. Notice that 16 plus 12 is equal to 28, and so we can use this property to substitute 28 for 16 plus 12. For my next step, I will use the subtraction property of inequality to subtract 3b from both sides of this inequality. Now, I can use the subtraction property of inequality again to subtract 28 from both sides of the inequality. Finally, I can use the division property of inequality to divide both sides of this inequality by negative 30. Recall that I must flip the inequality symbol whenever I multiply or divide both sides of an inequality by a negative number. As I said earlier, this is only one of many possible proofs. Please pause this video and look over the other 3 proofs in the handout. Now, let's look at some geometric proofs. For my next example, I will prove the midpoint theorem. You can find an example that shows what this theorem tells you on the second page of the document I told you to print earlier. Also, in case you're wondering, a theorem is a statement you can prove. When we want to prove a statement in geometry, the first step is usually to draw a generic picture that describes the if part of the statement. Note that this picture is a generic picture that illustrates the statement M is the midpoint of segment AB. When we want to prove a theorem, the if part of the theorem is the information you are given, and the then part is the part you want to prove. Therefore, for this proof, we can say that we are given that M is the midpoint of segment AB, and we want to prove that segment AM is congruent to segment MB. To prove this statement, we must start by stating the information we're given. Now, look at the bottom of the first page of the document I told you to print earlier. Since we just said that M is the midpoint of segment AB, we can use the definition of midpoint to say that this tells us that the distance between A and M is equal to the distance between M and B. Now, look at the definition of congruent segments at the top of the next page of the handout. We can use this to conclude that segment AM must be congruent to segment MB. Before we look at another example, let's talk about some of the notation I used here. Many people think it would be correct to write segment AM is equal to segment MB in statement 3. However, as the note that goes with the definition of congruent segments on the handout tells you, we are talking about pictures when we put segment symbols above the AM and MB, and it does not make sense to say that two pictures are equal to each other. On the other hand, when we do not put segment symbols above the AM and MB, like you see in statement 2 here, we are referring to the distance between 2 points. Since the distance between 2 points does involve a number, you should be able to see that it does make sense to say that the distance between A and M is equal to the distance between M and B. Also, I'd like to point out that many students try to say that the reason for statement 3 is midpoint theorem. However, you should realize that this is not correct because this is supposed to be a proof of the midpoint theorem, which means that I am going through a set of statements and reasons that should convince you that the midpoint theorem is true. And if I'm supposed to be convincing you that this theorem is actually true, I cannot use it as one of my reasons. For my next example, I will prove the congruent supplements theorem. You can find an example that shows what this theorem tells you at the top of the 3rd page of the document I told you to print earlier. We must begin by drawing a generic picture that describes the if part of this theorem. Hopefully, you remember that two angles are supplementary if and only if the sum of their measures is 180 degrees. You should be able to use this information to realize that this picture makes it look like angle 2 is supplementary to both angle 1 and angle 3. And so this is a generic picture that describes the if part of this theorem. As I said earlier, when you want to prove a theorem, the part that follows the if is the information you're given, and the part that follows the then is what you want to prove. Therefore, for this example, we can say that we are given that angle 2 is supplementary to both angle 1 and angle 3, and we want to show that angle 1 must be congruent to angle 3. Before we do a formal proof, it is often useful to convince ourselves that the statement is actually true. So, let's say that angle 1 has a measure of 75 degrees. Then, since angle 2 must be supplementary to angle 1, angle 2 must have a measure of 105 degrees. Since angle 3 must be supplementary to angle 2, this means that angle 3 must have a measure of 75 degrees. Since this tells us that angles 1 and 3 have the same measure, they must be congruent if we start out knowing that angle 1 has a measure of 75 degrees. Now, pick a different measure for angle 1. Pause the video and do some experimentation on your own. This suggests that this statement is probably true, but it does not prove that angle 1 must always be congruent to angle 3 in this situation. It is possible that we happen to pick some very special measures. So, now we must do a formal proof to show that angle 1 must always be congruent to angle 3 in this situation. We must start by stating our given information. Now, look at the definition of supplementary angles at the bottom of the 2nd page of the document I told you to print earlier. Since we just said that angle 2 is supplementary to both angle 1 and angle 3, we can use this definition to say that the measure of angle 1 plus the measure of angle 2 is equal to 180 degrees, and that the measure of angle 2 plus the measure of angle 3 is equal to 180 degrees. Next, we will use the substitution property of equality. The substitution property of equality is stated for you on the 1st page of the handout, towards the bottom of the properties from algebra. We said in statement 2 that the measure of angle 2 plus the measure of angle 3 is equal to 180 degrees, and so we can substitute the measure of angle 2 plus the measure of angle 3 for 180 degrees in the first equation in statement 2. Now, we can use the subtraction property of equality to subtract the measure of angle 2 from both sides of the equation we wrote in statement 3. Finally, we can use the definition of congruent angles to conclude that angle 1 must be congruent to angle 3. The definition of congruent angles is the first thing under the heading Angles on the 2nd page of the handout. Before we look at our next example, I'd like to talk about the notation I used here. Look at the note under the definition of congruent angles. When they write a statement like the statement you see in Statement 5, many students try to write angle 1 is equal to angle 3. However, as the note on the handout says, we are referring to pictures and not numbers when we write angle 1 and angle 3. Since it does not make sense to say that two pictures are equal to each other, we say that the angles are congruent instead. You can contrast this with the notation you see in Statement 4. In this statement, I am talking about the measures of the angles, and when I talk about the measures of the angles, I am generally referring to the degree measures, or the measures you might get when you measure the angles with a protractor. Thus, the measures of the angles involve numbers, and so we can say that the measures of two angles are equal. This should also tell you why I talked about the measures of the angles in Statements 2 and 3. I can add the measures of two or more angles together, but I cannot add two or more pictures together. Now, let's look at another example. In this example, I will prove the vertical angles theorem. You can find an example that illustrates what this theorem tells you at the bottom of the third page of the handout. You may also find it helpful to look at the definition of vertical angles stated above this theorem. I must begin by drawing a generic picture that describes the if part of the theorem. If you look at the definition of vertical angles on the third page of the handout, you should be able to see that angle 1 and angle 3 in this picture are vertical angles. Like I said earlier, the part of the theorem that follows the if is our given information, and so I can say that we are given that angle 1 and angle 3 are vertical angles. The part of the theorem that follows the then is what we want to prove, and so I can say that I want to show that angle 1 must be congruent to angle 3. Before we do a formal proof, it is often useful to do some experimentation and hopefully come up with a plan. So, I would like for you to pick some measures for angle 1 and then find the resulting measures of angle 3. Pause the video while you see if you can figure out why angle 1 must be congruent to angle 3. Now, to write a formal proof, we must start by stating our given information. Hopefully, in your experimentation, you realize that angle 1 and angle 2 must be supplementary, and that angle 2 and angle 3 must be supplementary. However, before we can state this, we must state that angle 1 and angle 2 form a linear pair, and that angle 2 and angle 3 also form a linear pair. The definition of a linear pair is found towards the top of the third page of the handout. Now, since we know that angle 1 and angle 2 form a linear pair, and that angle 2 and angle 3 also form a linear pair, we can use the linear pair postulate to say that angle 1 and angle 2 must be supplementary, and that angle 2 and angle 3 must be supplementary. The linear pair postulate is stated underneath the definition of linear pair on your handout. Now, note that we said in Statement 3 that angle 2 must be supplementary to both angle 1 and angle 3. Thus, we can use the congruent supplements theorem that we proved in the last example to say that angle 1 must be congruent to angle 3. The proofs that we have looked at so far have been in what we call a two-column format. Proofs can also be written in paragraph form or in the form of a flowchart. This is an example of a proof of the congruent supplements theorem in paragraph form. Notice that the statements and reasons are exactly the same as what you saw earlier. This is an example of a proof of the congruent supplements theorem in the form of a flowchart. Again, notice that the statements and reasons are exactly the same as what you saw earlier. This is an example of a proof of the vertical angles theorem in paragraph form. This is an example of a proof of the vertical angles theorem in the form of a flowchart. We can also prove statements using a type of proof called proof by contradiction. These proofs are also called indirect proofs. To prove a statement by contradiction, start by assuming the given information and the negation or opposite of the statement you're trying to prove. For my next example, I will show that if two distinct lines intersect, then they must intersect in exactly one point. I must start by drawing a picture to describe the if part of the statement. Next, I must decide what I am given and what I want to prove. The if part of the statement tells me what I am given, and so that I can say that I am given that lines M and N are two distinct lines that intersect. The then part of the statement tells me what I want to prove, and so I can say that I want to show that lines M and N intersect in exactly one point. In other words, I want to show that they intersect in one and only one point. I will begin by noting that the definition of intersection tells us that lines M and N must intersect in at least one point, and so I only need to show that they cannot intersect in more than one point. I will show you a proof of this statement in the two-column format, and then I will show you a proof in paragraph form and in the form of a flowchart. I must begin by stating the given information. Now, since I want to write an indirect proof of this statement, my next step is to assume the opposite of what I want to prove. So, I will assume that lines M and N intersect in at least 2 points, and I will call these points A and B. That tells me that lines M and N both contain points A and B. However, this presents a problem. On the second page of the handout, there is a postulate that states, through any 2 points there is exactly one line. A postulate is a statement that is accepted without proof because it is just too basic to prove, so we can use it here. Since we just said that lines M and N both contain points A and B, this postulate tells us that lines M and N must be the same line. Since we said in statement 1 that they are distinct lines, this cannot be true. Therefore, we have what we call a contradiction, and so I can conclude that my assumption must be false. This is an example of a proof of the same statement in paragraph form. This is an example of a proof of the same statement in the form of a flowchart. Now that you have an idea of what proofs are, I'd like for you to try a few problems on your own, and then come back and watch the video again.